Okay, let's talk about rationalizing with respect to roots. Now, to rationalize, quite simply, in many contexts, simply means to make rational. And that's what it means in this context as well, when we're talking about roots. And usually in math textbooks and math classes, we're talking about rationalizing a denominator of a fraction. You can also rationalize a numerator, but let's look at a case where we are rationalizing the denominator, or several cases. Let's just start with a simple example, 1 over the square root of 2, let's say. The square root of 2 is an irrational number. If it was the square root of 4, that would be 2. If it was the square root of 16, that would be 4. Square root of 36 is 6, so on and so forth. But not all these roots come out perfect. And in this case, the root of 2 is an irrational number. If you were to get a decimal approximation for that, you would see a non-repeating pattern in the decimals that go on forever. The decimals go on forever. There's a non-repeating pattern. This is an irrational number. So if I want to rationalize the denominator, it means I want to make this rational somehow. And here's a little thing about fractions. You know that if you multiply anything by 1, you get the same thing. You get some form that's equivalent to what you started with. Now I'm going to multiply by a particular 1, and that is root 2 on the bottom, root 2 on the top, root 2 over root 2. Anything over itself is 1. And why did I choose root 2? Notice the following when I continue this product. 1 times root 2 is root 2 on the top. On the bottom, root 2 times root 2, we can say is the root of 2 times 2, reversing the property that I showed you before where we were separating them. Now we're putting them together. This gives me the root of 2 over the root of 2 squared, or you could just say 4 if you want. Okay, any way you look at it. What happens in the end, the square root of 4 is just 2, so this becomes the root 2 over 2. And now I have rationalized the denominator. Notice that I changed the numerator, though, from a rational number to an irrational number. Pick your poison. Which one do you want to be rational? And it seems to me that in most textbooks, what they're focusing on is rationalizing the denominator. So there is one way to make something rational. Let's take a look at another example. How about 5 over the square root of 7? What would this look like? Well, again, following this pattern, I'm going to multiply by root 7 over root 7. Okay, and this equals 5 times the square root of 7 on the top over square root of 7 times square root of 7. I'm going to cut to the chase here and call that the square root of 49. And actually, we can cut to the chase even faster. The root of something times the root of the same thing is itself. So this comes out to 5 root 7 over 7. That's our final result right here, in that the denominator has been rationalized. A common temptation for students that I see is to say, doesn't this 7 reduce with that 7? No. If you're looking at a fraction that said, for example, 7 times something else, 8 all over 7, then indeed you can reduce those and say this is just 8. But the number up here is not 7, and that's the tricky part. This is 7, that is not 7. Although it looks like a 7, it is the square root of 7, which is some other number, some other irrational number. So don't do that. This is the final result shown right here. Okay, let me put out another example. What happens if we had, I'll start with pink this time. How about 5 divided by the square root of 5? Well, then we're going to start by multiplying by 1, and that 1 is a special one. It's root 5 over root 5. 5 times root 5 is simply 5 root 5. And on the bottom, root 5 times root 5 is 5. Now we really cut to the chase on this one. Notice here that there is something that we can reduce. There is a product on the top, 5 times root 5, which means I can reduce this top factor of 5 with this bottom factor of 5. I reduce them both by 5. This becomes a 1. This becomes a 1. And we end up with 1 times root 5 over 1, which is simply root 5 itself. And that's it. So these 5's canceled in this case. And there we go. We've rationalized the denominator. Let me see if I have room. I want to show a couple more examples. Let's do this. I think we have room. Go with blue. How about root 5 over root 7? We want to rationalize the denominator, so we're going to multiply by the special fraction root 7 over root 7. I'm choosing the denominator, okay, to pick those numbers. So then, root 5 times root 7 is what we have on the top. On the bottom, root 7 times root 7 is simply 7. And should I leave it like that? Well, the powers that be say no. We can combine these two guys to get the root of 5 times 7 on the inside, so that gives me the root of 35, and all of that over 7. And there we go. Here is our final result showing a rationalized denominator. One more, if I can fit it. Woo, this is tough. What kind of fun? What color? What color? I guess I'll start with pink. Okay. Suppose we had 2 root 5 over 3 root 7. Okay, kind of similar. I just wanted to show you how the numbers work out. What do we have? What do we do with this additional factor? Well, when we're rationalizing the denominator, we're still multiplying by, in this case, just root 7 over root 7. How come? Because the product here, root 7 times root 7, gives us just 7. It rationalizes what we're going to get down there. The 3 then gets multiplied also by the 7 that comes out. So we didn't really have to mess with the 3. This gives us 2 root 5 root 7 on the top over 3 times 7 from the root 7 times the root 7. I'm going to continue to simplify this to give me 2 root 35, where now I'm recombining these guys, over 3 times 7 is 21. And you might want to check as you're going through if anything cancels on the top from one of these numbers on the outside of the roots, one of these numbers down here that are whole or integers. But I don't see anything there, so this is our final result, the rationalized form of what we began with. Let me continue examples of rationalizing on another video.